Good morning. I'm going to continue with my discussion. I'm calling it the fine structure constant. But really what I'm doing is getting more and more into quantum theory. In fact, I'll get all the way up to quantum field theory in terms of the fine structure constant. I would like to do all of physics, quantum physics, in terms of that constant. I even have a gravitational equivalent for one as well, dimensionless number. So let's continue, and it can get pretty complicated beyond here, and so I'm trying to keep it simple as possible. I'm going to say more, so you're going to have to listen more. I'm going to write less, but I will carry out just derivations, all right? So what we're talking about is fine structure constant 4. If you like, so what happens is this. We did the old Bohr model. And we found the energy levels, the crude ones, for the hydrogen atom that gives the Barrow lines, and I wrote down what the Barrow lines were for n equals 1, 2, 3, and 4. Now, this m0 here is really the mass of the electron. But really, it's an approximation to mu. We can approximate mu with the mass of the electron because this is the formula for the reduced mass. The reduced mass comes into play when we work in the center of mass frame. Now the electron and the proton in orbit should be properly treated in the center of mass frame, but the electron is 1,840 times less than the mass of the proton, so this is approximately equal to the mass of the electron. So we can get rid of this now. We don't have to keep writing that. I've been using the mass of the electron in here all the time. Now when we translate now, we have to go to higher order in alpha, like alpha 4. When we go on successively higher orders in the fine structure constant, that means we're looking at the hydrogen atom more closely. To get these higher orbits, we can consider the following extra parts. Spin orbit coupling. The coupling of the spin of the atom with the orbital angular momentum, whatever that is. Go back and look at some of the quantum mechanics lectures I gave on this, although I haven't covered orbital angular momentum or spin yet. I will do. So, when we transform to the Schrödinger picture, what we do is consider expectation values. Expectation values of operators. Go back and look at my lectures on quantum mechanics to look at expectation values of operators and how operators represent physical observables in quantum mechanics. So this same result can be done quantum mechanically via the Schrödinger picture using finding the expectation value of the Hamiltonian. The Hamiltonian, go back and look at my classical mechanics for the Hamiltonian. But the Hamiltonian in quantum mechanics becomes the Hamiltonian operator. In quantum mechanics, as I explained before, there is an operator for every physical observable. The operator for the position observable is trivial, but that for momentum involves a derivative. d by dx in one dimension, nabla in 3 dimensions, and in the hydrogen atom, this would be in spherical coordinates. So that's what we get in the Schrödinger picture. So we will say that that's what we've got. The expectation value, and how to find it, that's in quantum mechanics. I've written down some expectation values. This is the symbol for expectation value. It's really, okay, we'll leave that out for now. That's the symbol for expectation value. And that at the 0th order, or the order alpha squared, is this quantity here. So now what we're going to do is we're going to go to order alpha to the 4th and evaluate the first correction to the kinetic energy due to relativity. So today we're not considering spin. Other corrections to the spectrum of the hydrogen atom would be, for example, like I said, the spin-orbit coupling, anomalous Zeeman effect, the Darwin term, the Darwin contribution. You say, well, wait a minute, Darwin? Yes, Charles Darwin. Due to Charles Darwin, not the Charles Darwin who went to the Galapagos Islands and wrote The Origin of the Species, but his grandson. Those other terms. And then eventually you hit the Lamb shift, discovered by another shift in the spectrum, a splitting between the S and P levels in the hydrogen spectrum, discovered by Willis Lamb and a fellow called Rutherford. Charles, I think, was his first name, not Rutherford, Rutherford, in the 1930s. And then thereafter studied by Hans Bethe, Fermi, Weisskopf, Schwinger, Tomonaga, and Feynman. The last 3 got Nobel Prizes for. For what? For quantum field theory, because at that level you have to introduce quantum fields. Now I skipped the Dirac equation. What we're not doing is the relativistic contribution as seen through the Dirac equation. We're doing a first order approximation, or a second order approximation if you like. So what we're doing is we're considering the adjustment to excuse me. Now, the Hamiltonian operator is the sum of the kinetic and the potential energies. And the potential here, of course, for the hydrogen atom is the Coulomb potential, and I'm writing mv as, well, it's going to be momentum. And here's our Hamiltonian. Well, these terms here plus this one constitute the fine structure constant. So that's the way we write our Hamiltonian, and this is actually an operator, and the p squared is an operator. Okay? So now that's what we're going to study. We'll study H and I'm writing H like that, where you won't see it written like that anywhere else. But I like to write it that way because it's more transparent. Let you get your head around that. I just rewrote this up here. Now the first thing we need to do is what? H naught gives E0. All right, we want to, okay. Now, Food for an immense lecture. And this is not explained very well in any of the texts, not satisfactorily at all. I'm just going to write it down for today. The relativistic kinetic energy of a particle is given by the following formula. Now this is the rest mass, and this is the rest mass. I'm just rewriting this by taking out a factor of a half, a factor of the square root of this. And I'll expand this out by the binomial theorem. I'll go to the third term. Now I'm getting rid of a factor of c squared here. That's really what we have there. And this gives the following. mc squared and higher order terms. Now we have to subtract the mc squared so that those terms cancel, and now we have our adjusted EK. So that's going to be the formula for kinetic energy that I'm going to use, and I'll find the contribution due to this. Alright, so I'm going to clear the board, let you get your heads around that. So here we have this whole thing. Now if I'm moving too quickly for you, all you have to do is scroll back in YouTube. That's why I don't mind erasing the board, because you guys can Oh, that's our kinetic energy adjusted. Now, and this is going to be H1, and this is going to be H0, including, of course, this part as well, okay? So we need the expectation value of this one here. So basically that's what we're heading towards, all right? So we're going to carry out a trick. We're going to write this. This is H0 actually. Now p to the fourth this object here. Now, a point that you guys might not notice, but as a technical point that's required for the following derivation, is that the Hamiltonian commutes with the 1 over r. So here's what we got for the p to the 4th. So therefore then, this object here the expectation value is all of this thing here. I think I've written it properly now. I've just substituted in this for p to the 4th. Now every time I get an expectation value for a h0, this is the quantity I get. And when I get an expectation value for 1 over r squared, this is what I get. When I get an expectation value of 1 over r, this is what I get. Now all I'll have to do is substitute all these objects in here. I'll get rid of this first. This is going to be positive this guy squared. Positive. And this is going to be this one. 1 over r squared is here. And 1 over n squared. No, I'm looking at the wrong one. This one, 1 over n cubed. So far, so good. And it's going to be minus this object here. Now, the factor of 2, okay, the factor of 2 here cancels my half, so I won't put it in. But I do have this part here. Now I'm just checking to make sure I've made. Okay, I'm missing some terms here. So 2 times this one, alpha h cross c, and this one here. Over n squared. So let's simplify these objects here. We don't need these, so I can move back up here. We don't need these. The only line we need is this one. So I get minus 1 over mc squared. This object here